All right, let's try this variation. Here they tell us that a 0.0500 gram sample of TNT, trinitrotoluene, is combusted inside a bomb calorimeter that contains 550 grams of water. Now, the initial temperature of our calorimeter and water is 23 degrees Celsius. It also tells us that the heat capacity of the bomb itself is 420 joules per degree Celsius, and the enthalpy of combustion is a negative 3,374 kilojoules per mole. They'd like us to determine, after this TNT is combusted, how hot does it get? What's the final temperature of our system in this case? Okay, so let's start at the beginning. We definitely are going to have a heat transfer in this case. The heat that's lost by this combustion reaction is going to travel outward. It's going to go into the water and it's going to go into that bomb. So I'm going to start off by saying heat that's lost is equal to negative heat that's gained. Okay, now let's fill in the specifics. Heat that's lost by the reaction itself, that combustion reaction of TNT. That heat that's lost is gained by, well, we need to read that problem closely. They give us information for how much water is in there and a specific heat capacity of the water. The water is going to be gaining some of that energy. But they also give us information about that bomb inside there. They give us the heat capacity of the bomb. It means that bomb is absorbing some of that energy. So we need to go ahead and take that into account as well. So heat lost by the reaction is negative heat gained by the water and the bomb. All right, we're going to leave heat of reaction alone. The heat that's lost by the reaction is negative. Okay, our water. Our water starts out at 23 degrees Celsius. It's just going to go through a temperature change. So since the water just goes through a temperature change and we have the specific heat capacity of the water, we're going to do an MCAT situation. So negative MCAT of the water. Now, what about the bomb? For the bomb, they give you the total heat capacity of the bomb in joules per degree C. So if we want heat from a total heat capacity, we don't use MCAT, we use big CAT, total heat capacity times the change in temperature of the bomb. Now, let's stop for a second and try to evaluate where we're at. We have the mass of the water. We have the specific heat of the water. We have the total heat capacity of the bomb. If we find the change in temperature here, we'll know how hot it got. We know it started at 23, and if we know how much it changes, we know the final temperature. So this delta T is what we want. What we need then is the heat of this reaction. How much heat is released here? Okay, so how do we get the heat released by the reaction? It's like we're doing this problem backwards. They give us, in this case, the enthalpy of this reaction. The enthalpy of the reaction is a negative 3,374 kilojoules per mole of octane that we explode. If we just go ahead and take our kilojoules per mole and multiply by the number of moles of octane that we actually combusted, we'll get the heat that was released. Then we'll know this number. So let's find the moles of octane that we actually combusted. We had a very small amount of octane. Our octane sample was 0.0500 grams. Now, for our octane, our trinitrotoluene, it turns out that 1 mole of TNT has a big molar mass. It has a molar mass of 227.13 grams. If we go ahead, take our 0.05, divide by 227.13, we end up getting for our number of moles 0.000220 moles. Okay, we're going to use that to find the heat released. Since delta H is heat per mole, that means that our heat is delta H times our number of moles. So we're going to go ahead and find our heat Q by taking the heat of this reaction, negative 3,374 kilojoules per mole, and we're going to multiply that by our moles, 0.123 zeros, a 2, 2, and a 0. Moles cancel out. That leaves us with the amount of heat released as a negative 0.743 kilojoules. Okay, cool. Now we know Q, except look at the units. This is in kilojoules. This is all going to come out in joules. We have a heat capacity in joules per gram degree C and a total heat capacity in joules per degree C. We really need to put this in joules before we continue. How do we get joules? Multiply by 1,000. If we multiply this number by 1,000, for every 1 kilojoule, there's 1,000 joules. Then we get our heat released, and we can plug that in over here. That is negative 743 joules. That's going to equal negative. All right, let's plug in our values. The mass of our water right here was 550 grams times the specific heat of water, that was a 4.184 joules per gram degree C, times our delta T. That's what we're trying to solve for. Plus, the heat capacity of our bomb here in this case was 420, and we're going to multiply that by the delta T. Okay, now let's do a little evaluation. Negative and negative, they're going to go ahead and cancel out in this case. So we'll have 743 equals, okay, 550 times 4.184 delta T plus 420 delta T turns out to be 2,721 delta T. All right, now we can solve for delta T by dividing both sides by 2,721. We're going to get a delta T, it turns out really small, of 0.273 degrees Celsius. Okay, so my initial temperature started out at, let's go ahead and write that down, TI started out at 23.000 degrees C. We know that combustion reactions cause our temperature to increase. Increase by how much? This much right here, our delta T. We're going to add 0.273 degrees C to this, and we're going to get a final temperature of equal to 23.273 degrees C. All right, lots of work there. I hope it made sense, and take care.